okay, if you need something. All right, here we go. So, what is calculus? What do you think? That's a W. What is calculus and why the hell are we making you do it? One reason is to filter out, I say especially for the computer scientists, we want to just test your mathematical maturity. That's one reason why we have you take it. And of course, as computer scientists, you don't need to be in school. You could develop software, you could hack into Russia, you could do anything you want to become a computer scientist. And one particular way is academia, right? So for most of the rest of us, we have no choice. You're not going to become an aerospace person dropping out of calculus. It's just not going to happen. But what is calculus other than a waste of money and time? I didn't say that. So what is it? How about a calculus? Do you know what a calculus is? It's a small stone, like a kidney stone would be a calculus. So if I drop a stone into a still pond, what do you see? Is it in the water? Yeah, what do you see? Good. What does it look like? What shape is it? Circle. So we see a circle in the pond. It depends on how clean it goes in. It should really be one circle. And what's happening? What's changing? Yes. So what's changing? Yeah, the size, more. Diameter is changing. Radius, of course, is changing. Circumference is changing. Area is changing. All with respect to what variable? What? No, what variable? What else is changing at the same time? I just said it. Time. So we're looking at the change in one variable with respect to the change in another variable. Listen to it. The change in one variable with respect to the change in another variable. What am I talking about? What's the simple math term I'm talking about? It could be a function, but it's simpler than that. Begins with an S, ends with a lope. A slope. Delta y over delta x. So we're talking about the change in y with respect to the change in x, right? So the study of how things change. Right? That's what we're talking about, the study of how things change. Yes, question? What's that? Absolutely. And if you need paper for homework or notes, I have it here. Okay. Let me know. So the study of how things change. So what do we calculate the slope of in our early math years? What do we calculate the slope of? a line. So our general picture of what we're looking at is I have some function f of x, right? Of course, I'm in the xy plane. Until Calc 3, I'm in the xy plane, okay? Never the imaginary plane. No imaginary numbers for us until advanced calculus, which none of you will take unless you make a mistake of falling in love with math. Okay? So we're looking at a function, and what we're going to do is say, well, I'd really like to know, like if I was skiing on this hill, what the slope at that one point is, because that's what's called the instantaneous change. So you ever see the speed cameras, right? So like I live 10 miles away. I live down by the baseball stadium in DC. 10 miles, it takes me an hour to get here. So the average rate of change for me from beginning to end is 10 miles an hour, right? But at one point, I got a speeding ticket, and I was going 50 at that one point. So, right, think about it. The amount of change over time is average rate of change. The change at that very nanosecond, even though they took two photos, because they're doing a slope again to see how fast I'm going, but they're really close together. And so that's the idea. I'm interested in the slope at a single point, and this guy is called a tangent line. The slope of that line is how I'm changing at that 1 second. And then, of course, we could have a secant line. And that's the one that we've been doing all along. We know how to calculate the slope of a line given 2 points. We're about to learn how to calculate the slope of a line given 1 point. And the process is very, very similar to what we did when we calculated the slope of a line with 2 points. So our secant slope, do you remember secants and tangents from high school geometry? Secants cross the circle twice. Tangents touch the circle once. Same idea here. So secant slope, right, is the slope of a line through 2 points. And then our tangent slope is the slope of a line through 1 point. Okay? So if the computers are a distraction to you, you can just turn off the monitor. Don't log out, right? Because I'm going to ask you to go on Desmos soon and do something. The secant slope is called average rate of change, right? And the tangent slope is instantaneous rate of change. So, how do we do this is we need something called a limit, and that's our whole first chapter is limits. Oops, chapter 2. Limits. So we've got lots of ways to talk about limits. And what is the limit that I'm going to be talking about? You can watch me do this real quick here. I guess I'll do it on Desmos. I am going to have you do this today. But not right now. I'm going to do it too fast for you. Nice. So I'll put in f of x equals like, well, let's say sine of x, right? And then I'm going to plot 0, 0. Because I'm interested in the slope at 0, 0. What do you think the slope is at 0, 0? Like if I was skiing on that hill, what would be the slope of my skis? Everybody understand skiing? Yep, on a snow-covered hill, yes? Everyone okay with that? So imagine I'm skiing that way. What's the slope of my skis right there at 0, 0? What do you think? Yeah, 1. Do you see it? No? Yes? Well, what I want to do is pick an arbitrary point. So a comma sine of a. And you can see what I'm going to do is I'm going to connect those 2 points with a line, right? How do I do that? So I have 0, 0 as x1, y1. I have a sine of a as x2, y2, right? To get a line, I need what? Y minus y1 equals m times x minus x1, right? Yes, does this all sound familiar to you? Hello? There's only 10 of you. You can't hide from me. Does this line sound familiar to you? This is called the what form of the line? Point slope. So I need a point, and I got it. In fact, I have 2. And I need a slope. I don't have a slope yet. I have to find my slope, right? What is that? y2 minus y1 over x2 minus x1. So just sine of a over a is my slope. So I'm going to use this point and this slope to get my equation of my line. Y minus sine of a equals sine of a over a all times x minus a. Is that okay with everyone? There's only 7 of you. I'm a Pisces. I need attention. I just need you to acknowledge that you're okay here. Anybody not okay? Fine, I don't want to talk to you either. All right, I'm typing that in. Y minus sine of a equals sine of a divided by a all times x minus a. This is what I will call my secant line. I can control it by taking this 1 point and moving it, or I can control it by moving my value of a over here. I would like to look at the slope of just sine of a over a. And when a gets to 0, right? When a gets to 0. So look at it right now, 0.97, right? Can I move it with the mouse? No, no. Oh yeah, I was moving it, right? No, it wasn't. So when I get to 0.1, it's 0.998, right? And when I get to 0, can't be done. This is the issue, right? This is the issue. How do you calculate a slope with only 1 point? You can't. We need calculus. But what we're going to do is we're going to estimate right now. So look, 0.9995, 97, 98, 99, and then look down here, right? 0.97, 0.98, 0.99. So what has to be, where is it going? In the middle is 1, right? Our guts are very our instinct is very connected to the universe, very connected to mathematics. We know it's 1, but how do we show it, right? And so that's the idea. This piece is going to become part of your dynamic secant line. Let's try and spell here, secant line. Dynamic secant line. We'll talk about that later today. Nice. So we're talking about limits here, okay? So we'll first talk about an informal definition of a limit. So our informal definitional limit is simply a predictable height of a function. So the limit as x goes to a of f of x equals L, and L is a real number. So all we have to do is be able to find a height of a function. It's really that simple. And so we can kind of think of this graphically, numerically, and algebraically. Don't let me go too fast. I can always go back to a page, right? And I'm never in a hurry. I like to say I'm Polish, I'm not Russian. Even if I was Russian, it's pretty funny. If I'm Russian, but I'm not Russian, right? So I'm not in a hurry. I know I can get the whole course done, even if you ask me a gazillion questions. So we want to talk about graphical limits first. So we want to know the limit as x goes to 2 of 2x plus 3, and we want to know the height. That's all we want to know. What is it? What is it? 7? Yep. It's that simple. Of course, it better be that simple if I have just a function that's a line. But what are we actually doing here is we're saying, if I'm walking on this hill, right? And let me put my music on. If I'm walking on this hill and I'm walking up the hill as my shadow on the floor, right, is getting closer to 2. Yes, you with me? I'm walking up the hill. My shadow is getting closer to 2. What height am I going to end up at? 7. Same thing as if I was walking downhill, right? If I'm walking downhill and my shadow is getting closer to 2, what height am I going to go to? 7. I don't actually have to get to 2. I have to get as close to 2 as I can. Remember what happened with my sine function? When I actually got to 0, I got undefined. So what we're doing is we're going to guess numerically where we think we're going to be. So it's kind of telling me that I have to check limits from the left and the right, right? So the limit as x goes to 2 of 2x plus 3 equals 7 if and only if the limit as x goes to 2 from the left, that's a weird notation, of 2x plus 3 equals 7. And the limit as x goes to 2 from the right, look at that notation, of 2x plus 3 is also 7. Yes, well, what we do is we explore these. And then we want to write that. So, but I have to predict this, right? I'm not actually getting there. Does that make sense? I'm predicting it. Like, if I walk halfway to the wall, then halfway to the wall, and then halfway to the wall, will I ever get there? Nope, never did. Because halfway, right? It's always going to be some number, right? But can I touch the wall? Oh yeah. So, but I'm trying to make a prediction, right? And that one's called Zeno's paradox, that I have an infinite number of unachievable steps that can be achieved. So graphical is pretty damn easy, right? Graphical is pretty damn easy. I don't test you on graphical limits, but you're going to use it to check yourself, right? You're going to use it to check yourself. So take a look at this function. Absolute value of x over x. Where do you think I'm interested in this limit? At what number is this limit interesting? Zero. 0 is where it's interesting, right? So this particular limit at 0 doesn't exist, but to the right it's positive 1 and to the left it's negative 1. So as I'm walking to the right, what number do you think I'm at? It's definitely negative, right? Negative. What number's close to 0 but negative? Negative 1 is not very close. I want to be very close. 0.9 is closer to 1, negative 1, right? I want to be close to 0. Yes, 0 is negative 0.001, sure. Can I get closer? Yes. Can I get even closer? Yes. And what height will I be at the whole time? Negative 1. And I'll never get to 0. I never get to 0. if I'm walking from the right towards 0, now I'm at like 0.1, 0.01, 0.001, 0.0001. What height am I at the whole time? 1. So can you predict where I'm going to be at 0? Can't predict. On the left, I'm always at a height of -1. On the right, I'm at a height of 1. You cannot tell me where I'm going to be at 0 because you don't know which side I'm walking from. And they have to meet up, right? So here, the limit as x goes to 0 from the left of f of x is -1, and that does not equal 1, which is my limit as x goes to 0 from the right of f of x. You with me there? Graphical limits are easy. Find the height from the left, find the height from the right. If they match up, you got it. What's the difference between my two functions here? The first one is continuous, no gaps, no holes in it, right? The second one is discontinuous. When it's discontinuous, I have more issues. When it's continuous, it's pretty easy. Graphical limits are easy. If you look at our WebAssign, where the heck is it? Sorry. If you look at WebAssign, I don't want the textbook, I want the problems. Damn it. Homework 2 is graphical limits. Okay? Homework 1 is the one I really care about, algebraic limits, so I'm going to get to that very soon, right? Then we talk about graphical limits and numerical limits, right? I need, so let's talk about some algebraic limits. And I have to introduce something that will bother you quite a bit, but I'm asking you, just like in life, things bother you, you have to get over it, right? And you have to try and deal with it, okay? But algebraic limits, what we're going to try and do is replace a function with another function unless I can just plug in, right? So let me come back to algebraic limits, sorry. Let me talk about this formal definition of a limit. We're going to say that the limit as x goes to c of f of x equals L if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that the absolute value of x minus c is less than 0 implies the absolute value of f of x minus L is less than epsilon. Listen to it again. If I have a function and my x is getting closer to a value, then the function should get closer to a height L, right? If that is happening, absolute value of x minus c is less than 0 implies f of x in absolute value is less than epsilon. I'll write it down for you in a second, okay? Word for word. Epsilon and delta, yes, but yeah, epsilon and delta are like, they're Greek letters, now variable. Positive and very, very small. Okay? What's this guy say? Oh, sorry. I made a mistake. Sorry. 0 is less than x minus c is less than delta. There it is. What is that one saying? What's this guy saying? If I say it's greater than 0, what is going on with x and c? That's, it cannot get to c. I get closer and closer without ever getting there. Right? And what the hell are the absolute value given? So if I'm negative, it goes positive. If I'm positive, it goes positive. That's the left and right side. Epsilon is related to what variable? X or Y? Y. Right? That's a height, right? That's a Y value, right? Epsilon is related to Y. Delta is related to what variable? Well, it's not Y. X. For every dartboard, or the arrow, right? For every target, yes? Can you see the target out in the distance I'm shooting the arrow at? Yeah? There exists a bullseye Yes, you with me? Everybody understand this? Not everybody plays darts, but I think you can all see like the archers in ancient times, right? Shooting arrows, yes? For every dartboard, there exists a bullseye such that if we restrict the arrows to a certain width, what width? I'm throwing darts at the board, right? And I put up, you ever go bowling and they put up the gutters for the little kids? They don't get right? They put up the bumpers. You know what I'm talking about? No? So I'm going to put up a restriction so that when I throw, it can't move outside of that distance. Okay? You with me? So I put up this restriction so I can't move outside of that distance. So imagine I threw a bunch of arrows, right? Like here, 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 right? Nothing is allowed to land outside of that. If we restrict the arrows to a certain width and they stay on the board, then what must we hit? The bullseye. So even though some of these miss the bullseye, right? How big is epsilon? So it gets smaller and smaller. Remember, I can make any size dartboard I want. So I want to get the dartboard to go to what? Nothing. That means each of these dots end up right in the center at the bullseye. So let's look at the limit as x goes to 2 of 2x plus 3 equals 7, right? And I'm going to say let epsilon bigger than 0. So just give me a positive number. 0.01. Small dartboard, right? Pick delta equal to epsilon over 2. I just know that because I've been doing this for 40 years or so. Let epsilon equals be positive, and give me a delta of epsilon over 2. Assume 0 is less than x minus what? What's my c value? Yeah, I thought you were telling me peace. So x minus 2 is less than delta, and show that f of x minus 7 is less than epsilon. Well, what is f of x? What is f of x? Yep, 2x plus 3 minus 7, that's L, right? Which is what? 2x minus 4, yes? So a 2 will factor out of that, yes? Notice that my delta piece shows up. And I already know that delta, that's got to be less than delta. So this is less than 2 delta. Do you see the 2's are the same? Do you see these two? This 2 is that 2, right? And this delta is that delta. But what did I let delta be? What was delta? What did I pick delta? Epsilon over 2. So I got it. Look, epsilon is greater than f of x minus L. Everyone okay? Anybody having a panic attack? What the hell's going on? Anybody saying, what the hell's going on? Yeah. Yep. I'm going to do it several more times. So, but the idea is, and I'll show you, I want to show you graphically too how this works. Well, here, I can do that right away. Let me do that right away. I'm using a program called Sketchpad. This is an expensive program, but you can view something similar on Desmos. So I want to change my function. Where the heck is my function? Oh, there it is. To 2x plus 3. And I'm interested in my center to be at 2, 7, right? So what I have done here, so A to B is my epsilon, A to C is my delta. Dartboard and bullseye, yeah? The epsilon I picked. Sorry, the delta I picked. You see it? There's that width I want to restrict to. Yes? But look at the bold green in between. Maybe I should change that color. It's not giving me the color I want, but that's fine. Do you see this bold piece of the function? Right? Do you see it dark green between my delta pick? Yes? Do all of the places on that dark green line hit the dartboard? Does every point on that dark green line hit the dartboard? Yes or no? Simple. Does this point hit the dartboard? Yes. Does this point hit the dartboard? No. So when I shrink my dartboard down, will I guarantee I hit the bullseye? No, because some of the darts are off the board. But if I pick it to be epsilon over 2, so if I cut this thing in half, right, or even better, now look at this point. Look at the dark green line, right? Does every point on that dark green line fall inside of the target itself? Not the bullseye, the target. Yes. So when I shrink my epsilon down to nothing, what happens? What did I hit? Center. The bullseye. I got the limit. You'll see another one, okay? I usually take a break, but today we kind of almost started at 12:30, so I don't. So we had our break first. But if you need just to use the restroom, feel free, okay? All right, I want to do some algebraic limits. I have to do numeric limits, and I have to look at when do limits not exist. Here we go, algebraic limits. Let's look at the first one. Let's look at f of x equals x squared minus 4 over x minus 2. Where is this limit interesting? Yeah, 2. So I'm interested in the limit as x goes to 2 of f of x. But what I'm going to do algebraically, and there's 3 situations for us. Factoring, conjugates, or, don't tell me, LCDs. Factoring, conjugates, and LCDs. Those are the only things we're going to have to do algebraically. This one is obviously factoring. right? I get x plus 2 times x minus 2 all over x minus 2, correct? And so this turns into what function? X plus 2. We'll call that guy g of x. It's only equal if x does not equal 2. F of x and g of x are exactly the same, provided that x never get to 2. In fact, and you can do this on Desmos with me, if I go to Desmos and I graph f of x as x squared minus x, minus 4, all divided by x minus 2, I graph the line. At 2, I see a height of what? 4. So it looks like my limit is 4. And it is that simple. Right? And remember, when I'm doing these limits, I never get to 2. I never get to x's c. Right? But what am I going to type in? My function g of x, which I got as what? X plus 2. Yes? Can you see any difference between g of x and f of x? Red light, green light. Can you see any difference? Hello? No, right? So this is now going to equal the limit as x goes to 2 of x plus 2, which is just 2 plus 2, which is 4. When I can plug in, plug in. When I'm allowed to plug in, just plug in. That's the simplest thing. Remember, we're trying to find the height of a function, right? We're trying to find the height of a function. How do you find it? We'll put the value inside and tell me the height. So, but what's the difference, right? What's the difference? F of x and g of x are identical, provided that x is not 2. When x is 2, I can't plug in here, but I can plug in here. And so when I do it, once I plug in, notice the limit is gone. I already know the height is 4 here. And that's what I get. Algebraic limits, what we're trying to do is rewrite a function as another function where I can plug in. Yeah, question?
Yeah.
Mike?
So the first 2 was given. That's the limit, right?
This one.
Yeah,
Yeah.
It was given.
Yeah, but I'm also going to be asking you all the time, when is this thing interesting? Well, at 1, it's not interesting. I can just plug 1 in, get the height, right? 0, it's not interesting. I can plug the height in. I can plug 0 in. I can't plug in 2. Because I'm dividing by zeros, right?
Oh, so you're just saying what's the line?
Exactly. So, and I won't ask you, I mean, like the 2x plus 7 one, 2x plus 3, as x goes to 2, is boring. You can do that one right away, right? So, but I needed the formal definition here, right? I needed the formal definition here because what do I have? I have for every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than x minus 2, which is less than delta, implies x squared minus 4 over x minus 2 minus 4 is less than epsilon. So I have the delta that makes this work. I have the delta that makes this work because what did I get? right? Remember, I replaced my function, right? Remember, this was my function f of x, right? This is my function g of x. What does this become? X plus 2 minus 4, what does it become? Huh? But remember, I can never let x go to 2. But now that I have x plus 2 minus 4, right? That's x minus 2. And now when x is 2, what number do I get in here? When x is 2, what number do I get in here? 0. Is that less than epsilon? Epsilon is a positive number. So it works. By changing my function, replacing my function with a replacement function. How am I going to get the replacement function? Factoring, conjugates, LCD. Sometimes a combination of two of them or all three of them. Let's do another. Sorry, don't tell me. I'm losing my mind for a second here. Yeah, that's fine. So where's the limit interesting? 3. We want to find the limit as x goes to 3 of f of x. And in this case, we're going to use a conjugate. Whenever you see a radical, a square root, sorry, you're going to use a conjugate. So we're going to multiply by oh, I'm sorry. I'm screwing up. Give me a chance to redo it, okay? There we go. That's better. All right, write it down now. Sorry. So radical x minus 3 all over quantity x minus 9. And of course, 9 is our interest here. If I plug in right away, what do I get? What is f of 9? 0 over 0, right? And so what do we remember? What do we remember about this? 0 over 0, what is it? We had a word for it at alpha 2. Say it again? Undefined. But we actually know what undefined means, hopefully. It means plus or minus infinity. Right? When I have a line, vertical line, slope is either infinitely positive or infinitely negative. Can't tell. Can't tell if it's positive or negative. So this is something for us called an indeterminate form. And when we see it, we're going to know we have to do some algebra. So what we do is we use the conjugate. So the conjugate is x, radical x plus 3 over itself. What am I actually multiplying by there? What am I multiplying by here? In blue, what number am I multiplying by? What is it? No, what number?
Oh.
1. So I'm not changing it, right? I want to leave the downstairs alone. And manipulate the upstairs. If you remember from algebra, a plus b, quantity a plus b times quantity a minus b is a squared minus b squared. So I get what? I get x minus 9. Right? Do you see that? I get the x here. I get a plus 3 rad x minus 3 rad x. They go away. And then negative 3 times positive 3 is negative 9. And then this piece cancels. So I get 1 over square root of x plus 3. And there's where my limit's going to go. So this is the limit as x goes to 9 of my replacement function 1 over square root of x plus 3. And now I can plug in, right? Now I can plug in. I can plug in to square root of x is square root of 9. And I get 1 over 6. Let's look at that one on Desmos. I'll wait for you. So when I'm doing algebraic limits, I want to find a replacement function, right? How do I do that? Algebra. Factor, conjugate, LCD. Sometimes both. Sometimes all three. Let's look on Desmos. F of x was what? Square root of x. What I had x minus 9 downstairs, right? Upstairs I had, instead of x squared, I had square root of x. Squirt, S-Q-R-T, x. So you can see graphically, now there's no left and right here, right? So I only need a left and right if there is a left and right. But because of the square root function, right? Yeah. And what did I get for my limit? 9, yeah, 9 comma, 9 was the x value, right? And I got a height of 1 over 6, yes? Boom. Oh, there is a left and right there, sorry. But when I'm doing the algebraic limits, the left and right will work out for me. Okay? Well, it will or it won't, but in this case it does. I keep using 2. Don't let me confuse you by me using 2 over and over. Just whatever. So obviously we're interested in this limit at 2, but when I plug in I get 0 over 0, right? Everyone agree? So I can't plug in. I want to be able to plug in to get the height. So I've got to manipulate, and I manipulate in this case with an LCD. How do I know when to use what? Well, if you see a radical, use a conjugate. If you see a fraction, use an LCD. If you see a polynomial, factor. It's that simple. So what's my LCD here? 2x, right? Everyone agree with that? I look at all my interior denominators and multiply them together, right? Yeah, you with me? Everyone okay? So the limit as x goes to 2 of f of x is the limit as x goes to 2 of 1 over 2x. And that one I can just plug in, so I get 1 over 4. I want to check this graphically. I'll do it on my calculator so you can see it. If you need me to go back, tell me. I know this is tough to see. It's as big as it gets. So in y equal, I'm putting in the function. What did I had? I had 1 divided by x minus 1 divided by 2. All of that divided by 2 minus x. Notice I'm putting things in parens. I look at my graph. I know I'm going for 2, right? X is 2. And what I do is, I think I do trace, and I say x is 2. And I'm supposed to be able to see it blinking. Sorry, hold on. There, okay, x is 2. No, that's not working. I have to look that up on the calculator on the web, but here I'll do it here. F of x equals what? 1 divided by x minus 1 divided by 2. All of that divided by 2 minus x. And then I can plot the point 2 comma 1/4, was it? There it is. So nice way to check if you're right? Easy to check. So I need you to do some research for me. How do you plot a point on a function in a TI 82, 83, 84, right? I know how to do it another way, but it's too complicated. I turn my stat plot on, and I go into my stat menu, I edit, I put in 2 in the X, and I put in 0.25 in the other, and I look at my graph. And now, right, but that's the long way, there's a shorter way. Look it up, okay? If we're in the other building, we're going to be doing everything on our calculator. If we're in this room, we'll do it on Desmos. Okay? All right, your turn. You ready? Algebraic limit. F of x is going to be 1 over square root of x minus 1/2 over x minus 4. And I'm interested in the limit as x goes to 4. On your mark, set, go. It's easier to clear the fractions first before you deal with the conjugate. Sorry, radical then it's conjugate. Fractions first here. What's our LCD? What's our LCD? Anybody have it? Two, yeah, 2 root x, yep. 2 root x over itself. Everybody close? Like 2 red X down here, purple, and it's still 2 red X here. That 2 red X can't go away. Downstairs. So I'm looking at the limit as x goes to 4 of f of x. Turns out to be the limit as x goes to 4 of my g of x, 1 over 2 rad x times quantity x, 2 plus rad x. And now all of a sudden I can plug in, right? I can plug in the 4. So it looks like I get, oops, and it's a negative, sorry. So I get negative 1 over 2 times 2 times 2 plus 2. I get negative 1 over 4 times 4. I get negative 1 over 16. Anyone get it? Uh-oh. Uh-oh. No one? So we should talk about the algebra, right? Yes? Step 1. How do I know to use the LCD? What do I see in my problem? Fractions. Then I see fractions within fractions. I want to clear out, I want to turn it into a single factor numerator over a single factor denominator, and I do that with an LCD. How did I get 2 rad x? Well, my only interior denominators are 2 and rad x. So I multiply them together, and that's how I get my LCD. I distribute through upstairs, right? See in this line? I distribute the 2 rad x to the numerator. I did not distribute the 2 rad x to the denominator. Why? I know what I'm trying to do. I'm trying to clear fractions. So put it where there are fractions. So upstairs in black, I get 2 minus rad x. Everybody okay with that? And then downstairs is the same as here. And now, how do I know I need a conjugate? What am I seeing? Radical square root. When I see that, I need a conjugate. And the conjugate means change the sign. So 2 plus rad x over itself. With me? Hello? Question? I look at the interior denominators. So I look at my original problem, and I see I have a denominator of rad x, a denominator of 2, and a denominator of what? What's the denominator here? 1. So multiply them all together. 2 times 1 times rad x. Now I've got to distribute here, right? Or FOIL if you want. If you want to, it's a 4-letter F word to me. That's fine. So I distribute, right? 2 times 2 is 4. I got a positive 2 rad x and negative 2 rad x. They go away every time. That's why I use the conjugate. And then negative rad x times rad x is negative x. This is another part that's going to get a lot of you. 4 minus x and x minus 4 are opposites, so when they cancel to what number? Negative 1. There's my negative. Cancel the opposites that are negative 1. All right, numerical limits. Sure, always. You want to do another one before I do numerical? Yeah. Okay, you're on your own. You ready? I want the limit is x goes to 1 of x cubed minus 1 over x minus 1. So I usually do notation like this. I'll call this inside star, and then I'll manipulate star, right? So I don't have to keep writing limit over, right? I just want to work on the function. You make it 3? Can't factor, huh? Scaring me. Uh-oh, right? Algebra. Anybody get it? Nice. Arsenal? Yes? Yes? Nice. So if you forget how to factor, you got to go back and review all your factoring, right? You're going to have to go back and review your factoring. I personally use synthetic division here. Do you want to see that? So I'm going 1 into 1x cubed, 0x squared, 0x minus 1. And I bring down the first term, and then I multiply and add. Multiply and add. Multiply and add. And I can see my x squared, right? 1x squared plus 1x plus 1. Long division would work, right? Long division would work if you forget how to factor that. You want to see the long division? So I'm doing x minus 1 into x cubed plus 0x squared plus 0x minus 1. Right? X into x cubed is x squared, right? Change my signs and add. So I get x squared plus 0x minus 1. X into x squared is x. Change the signs and add. So I get x minus 1. Oh, plus 1. Pre-cal. The pre-cal will haunt you. Synthetic division, long division, right? Got to be able to do everything from pre-cal. You okay? When I ask you if we're okay and no one looks at me, I think you're not okay. Thanks. Like when I say to my girlfriend, "Do you love me?" and she doesn't look, she won't look at me or answer me.
I want to have a question.
Yeah.
Basically, you saw that x3 minus 1.
Yeah, x cubed minus
The
1.
two imaginary things and kind of divided it out.
So you're talking about these zeros here?
Yeah.
Yeah. Yeah, not imaginary, but
I mean, not
yeah.
But like, they're like there, but it's
Yes, exactly.
Okay. Thank
You remember doing this in pre-cal? No?
I had it last time.
You didn't do synthetic division and long division and difference?
All we did was find the cosine.
No, that's trig. You didn't do exponentials and logarithms?
Pre-calculus?
Yeah.
We did logarithms and like other kinds of stuff. But like, it was mostly just somewhat decimals, but that's all. Sometimes we did like, mostly like trying to do stuff.
Okay. Should have done polynomial functions, rational functions, exponential functions, logarithmic functions, and trig functions. All right, numerical limits. Let's do one we did already, right? And we'll do this on the calculator, and we'll do it on Desmos, right? Two of you don't have a calculator yet, right? Let's get one, okay? If we're stuck in the other room, you're going to have one. We don't have computers down there, okay? And sometimes you don't want to have to use Desmos to do 7 times 23, you know? You want to just have a calculator with you all the time. And you can't use your phone on a quiz or a test. So no phone calculators, okay? You can use a formula sheet. So you're going to start building your formula sheet right away because our first quiz is Wednesday on algebraic limits, right? You'll probably have one where you have to factor, one you'll need LCDs, one where you need a conjugate, or one where you need a combination, right? There are a bunch of problems for you to practice besides doing the ones over from class. If you look at our Blackboard site and you go into past exams and etc., and you go into chapter 2, there's a chapter 2 review and solutions. And number 2 is all algebraic. Make sure you do all of them. Say again? Yep. If you prefer things printed out, you can always grab something here and print it right there and take it with you, take it home. Okay? If you go back to that same content and look at all my old quizzes for chapter 2, there's a numerical, there's an algebraic, right? There's an algebraic. There's an algebraic. So I'm not, right? I'm not trying to, there's a whole bunch there. There's a whole bunch of quizzes. It's like every semester. I've only been here for, this is my 4th year here. And I teach summers too, obviously. So it could be 3 times 4 semesters. It could be 12 semesters of tests and quizzes and etc. Right? So it's a lot, but you got to stay organized. You got to make sure you practice. Let's do a numeric limit, right? Yes, question. Exactly. Anything you want. So if you're really weak at trig, you better have the unit circle on there, right? Front and back, and edge. I'll let you use all 6 sides. The edges too. And you can use a magnifying glass. It's fine with me. I'm joking, but you gotta write small. I personally would have probably 12 pages and then scan them and then print them 6 pages per side. That's what I would do. Put some actual problems on there, put some step-by-step on there, right? Any kind of notes. All right, numerical limit. Let's do one we did already. Let's see, I had the limit as x goes to 2 of x squared minus 4 over x minus 2. And we got the answer of 4, correct? Yes? So we want to look at the limit as x goes to 2 from the left. And we're going to do an XY table for that. Usually when you get to gas station money, you're done. Gas station money is 3 decimal places, right? They always charge you like $4.999, right? So that 3rd decimal place is you usually will get to it by then. So we want to get as close to 2 as we can from the left. That's 1.9, 1.99, 1.999. I should get there on that 3rd step. If we look at the limit as x goes to 2 from the right, of x squared minus 4 over x minus 2, I want to get close to 2 from the right, $2.10, $2.01, $2 and gas station, 1/10 of a penny, right? And then, of course, one more, but usually our calculator, you can't even handle it. We can do it on Desmos as well. Let me do it on the calculator first. Okay? I know a couple of you don't have your calculators yet, but make sure you practice this. The thing is, I'm going to teach you how to check everything. So by the time you leave the test or the quiz, you should know you're right. When you're doing your homework, make sure you're getting them right. If you're not getting them right, you're wasting your time. Do one problem, look at the answer, and make sure it's right. Or do one problem and then check it with the calculator or Desmos, right? So watch how I do this. First of all, in y, you got to turn it on, Robert. In y equal, I want to type in the function. It's a multi-term function, so I need to make sure I wrap things in parentheses. So numerator, parenthesis, x squared minus 4, close parenthesis, divided by parenthesis, x minus 2, close parenthesis. I want to see the function, especially at the place I'm interested in the limit. So it helps to start with Zoom Standard, Zoom 6, and take a look at the function. Remember, I had plotted another point on there. I still have it open. Let me just turn it off real quick. Stat plot off. Now, I want to go to second table set. Anybody doing this right now? Anybody doing this right now on your calculator? What the hell? I know two of you don't have one, but what the hell is everyone else doing? Oh, you left it at home. That's fine. You have it though. Okay. So I say independent. That's my x variable. I set it to ask. I go to second table set and set my independent to ask, and then go to second table. And so what did I have? 1.9, right? 1.99. 1.999. At that point, you should know where it's going. And it's pretty obvious it's going to 4. And I want to check the other ones. 2.1, 2.01, 2.001. Again, really obvious where it's going. It's going to 4. These things are so easy that I don't have to ask them on quizzes or tests. But you have it there to double check yourself, right? That's the key, is that you're able to double check yourself. So I ask you to do this limit algebraically and show it to me. And then for your own sake, you should either do it graphically or numerically to check it, right? How are we feeling? You feeling okay about things? Yeah, I have an answer.
So like when you're asking this question at test, I have to write the whole limit thing, or could I just like say?
So I'm not going to ask numeric, right? I'm going to ask algebraic. So just the way I did it a couple of different ways, you can pick one of those, or you can watch someone else do it. Right? Let's talk about one last thing and then get the hell out of here, right? We're going to meet tomorrow in our regular classroom, okay? Yes? Bring your calculators, right? Start working on your formula sheet. You had one little research thing to do, how to plot a point on a TI 8384. It's simple. There should be several ways. You want to find the easiest way. I did it with stat plot. Not that easy, okay? When do limits fail to exist? Three possibilities. There's a gap. Don't go on that roller coaster, right? It's infinite, unbounded, or the most interesting one, the oscillation. right? So there's a funny limit, a couple funny limits. Well, funny to me, but remember Grandma's basement? Ever been down in Grandma's basement and she had a light with a string? Did you ever see that? You pull the string, the light goes on. Pull the string, the light goes off. No. Keep doing it forever. What's happening? Light on or off at the end? What? On? Anybody else? What? Forever. Can't tell. I like that answer. Depends. It's off. It's off because the light bulb burnt out. Funny, right? But that's an oscillator. You can't tell, on or off, right? Cannot tell. I'll show you a Google limit if we have time, but this is, so when do limits fail to exist? We have a jump discontinuity. So we saw that with f of x is the absolute value of x over x, right? And that particular one, right, had a height of -1 to the left and a height of +1 to the right. What's my formal definition? What's my informal version of the formal definition for every what? Epsilon, but what was my informal piece? For every dartboard, right? For every target or dartboard, yes? For every single one, even this one, right? If I restrict, the width, the pieces of the function had better still be on the dartboard. But look at this part of the function right there. Is it on the dartboard? No. So I picked an epsilon smaller than the gap. There's no way to find a delta. Everything will stay off the dartboard no matter what. You hearing that? You see that a little bit? There's no way if I shrink down that dartboard to nothing that there's pieces of the function still on the dartboard. And that's what I need to hit the bullseye. I need to have some of the arrows be stuck on the dartboard, right? Unbounded. So f of x equals 1 over x squared as x goes to 0. What's the thing about my limit? What's special about my limit? The limit as x goes to c of f of x equals L, which must be what? What kind of thing? What's L? What the hell is L? What is it? What is L? A what? Okay, in this case, no, right there on my paper, when I'm writing this definition, what am I saying L has to be? What's that bold R mean? A real number. It has to be a number. Infinity is not a number, right? It's a concept, or it's a car. It's not a number. It has to be a number. So if I get an answer of positive infinity, right, we say does not exist. So the limit as x goes to 0 of 1 over x squared equals infinity, but we really rather write DNE, does not exist. The last one is called an oscillator. Are we okay? We okay here? oscillation. So for example, y equals sine of 1 over x. This one is hard to see on the calculator, easier to see on Desmos. So let's go to Desmos with this one. So you can pretty much see, oops, sorry. Come on, Robert. You see how dense it is in the middle? How dense it is in the middle? It's going up and down so fast, right, that you can't even tell where it is. And so it's easy for me to show you this numerically and with the formal definition, right? At 0, it's going nuts, right? Yes? So what I do is I pick an epsilon smaller than that, and aren't I guaranteed points off of the target? No matter how thin I make my delta, right? Aren't there always going to be points out of the target itself? Yes. So it does not exist, the limit does not exist. Let's look at this one numerically. Can I do it with a sine? Yes. Am I allowed to type there? Oh yeah. Let's just do from the right, 0.1, right? And then 0.01. Yes? And then 0.001. And then 0.0001. You can tell it's bouncing between positives and negatives, right? 0.00001. Right? You with me? You can see it's not going anywhere. There's no clear way to guess at this one. I'm way past gas station money, and there's no clear answer, no limit. Guess what? We're done.